Let's take a look at boiler control strategies, and specifically I've got a module that is uh, called the 145 M11 M311 Boiler Control Strategy Module 1. And before we get started, I'm going to just preface this a little bit. Whether we are dealing with an older control or any type of the newer boiler controls, so much of the capabilities of these boiler controls from past as well as present are identical. There might be some very minor terminology type situations with a boiler manufacturer, for example, that you might have to read in their manual, or it could be the way they might do it or use certain criteria, but for the most part, almost all of them are the same. So it's just a matter of, so when I talk about this today, we're really speaking somewhat generically, no matter who the manufacturer is, and we'll get up on there. So let's take a look at the first part. So I've got two presentations up. The module that we're dealing with is that 145 M311, and the other one is the kind of a PDF, which is the 145 M310, and it's the control strategies. It's the PowerPoint that I normally use to go through this. So let's take a look at some of these, and we can kind of divvy it up and go from unit to unit here. So first of all, in the first slide that I have here, it talks about comfort and energy savings and high quality energy use. So we're going to hit up on some of that. So specifically in the boiler systems that we're dealing with, it talks about describe the four main objectives when you provide the best control situation. So first thing is, I think everybody is trying to control or provide some sort of let me change that a little bit. Everybody's trying to control a system, and so the customer is more comfortable. And I think that's pretty straightforward. And the ways that we do this are either we're going to control it by, control the air temperature, and that's typical of most spaces. And the other way to do it is to minimize expansion noises in the piping systems and also the materials, the building materials. So this, you'd be surprised if you don't have a system isolated how expansion noises can become an issue or a problem. From an energy saving standpoint, I think it's very straightforward that it is proven that if I can keep a boiler system running steadier with longer operating times and less cycling, I will save money on that operating of that unit. The other advantage that I get to do with this is that if I can cut back on the cycling, that's one way to save energy. The other way I can do this is if I can reduce the supply temps. So I'm talking about the temperature of the water that's leaving the boiler system and going out to the zones. And if I can reduce that, I will take care of everything that I do there. I can essentially take care of this, as well as I can take care of this, as well as I can take care of this. So this is definitely related. Now, it does require you to some extent on certain applications, when you do reduce supply temps, it's way more advantageous if you can have a modulating boiler system. But there are limitations within that. So the boilers themselves, some of them are single stage boilers where you're going to get all the BTUs no matter what. And so what will probably have a big effect on that is whether the boiler system will have an issue with having enough mass. And so a higher mass boiler system will tend to get a little bit longer cycle time because of the time that it takes to heat up the mass of that. And that the mass can include the weight of the boiler as well as the water in that system. So having zones large enough can also have an effect on that. So there's a lot of things that a person has to look at in the strategy of a system. Quality, that's kind of a salesy thing here when talking about high quality. And yes, we're certainly going to try to protect systems from excessive temperatures and things like that. But that's more, again, I'll leave that as is. Item D, incorporating ease of control for the customer and the contractor. Absolutely, that's really to our benefit. And for example, like things like they can incorporate automatic testing of the components. So if I run that boiler system and I go up to the system, it's not working, are there any diagnostics that helps me figure it out? So I like to see a status that would say, hey, what's calling? Oh, we have a zone demand, or we have a domestic water demand. So those things help. And then certainly from the troubleshooting standpoint, and that goes without saying. So the first one that I'm going to hit up on is in section 2. Now we're going to hit the second slide, and what we're going to talk about is essentially building space control heating strategies. And the first one is, why would I want to have that? Why would I want a control strategy that's necessary? So on this particular one, building space control strategies. And the first thing is without a doubt, we want to control a system that would maintain this a very steady building air temperature. We do not want swings. So and I'm talking about while we're occupied. When we're unoccupied, we're certainly going to incorporate setback, but we want to, while the system is running, we want to maintain very steady temps. And that's one of the big advantages that we've always had with hydronics. They've always done a good job of that. The second one, we talk about heat supplied must be equal to the heat lost. So that is challenging to do. It's very challenging to do. So I'm going to slide this on over and hit up on this second slide here. Now specifically, when we talk about the heat input equaling the heat output, now specifically, this is where the dilemma comes. Now this is the ideal way. You'd love the amount of, let's say that as your building is losing heat, because of the delta T, we know that the heat loss goes up. So that what the challenge that we face, and that can be all over the place, down in the ground, you name it. So the problem that we run into is, how do I get it so that the BTUs that I put to the emitters equals the heat output? So that is the issue. So the heat output, so this is what we really want to try to do. So the only way that I'm going to be able to achieve that is I'm going to need to have a strategy that will, let's say, limit the supply water temp. Now, in the previous module that we had talked about heat emitters, one of the things that we dealt with there with those heat emitters was if we can manipulate the water temperature going to each one of those heat emitters, we will indeed change the output of those emitters. So that's where this is ultimately why we want to manipulate the temperature of the water. And every heat emitter has a different little characteristic that is the other challenge that you have. So it's a lot easier to do the control of these systems when we have just one style of emitter. And that's kind of one way to look at that. From this standpoint, okay, we talked about lower output heat inputs lead to temperature swings. Well, let me explain a little bit what we mean by that. We'd say higher or lower heat inputs lead to temperature swings. So ultimately, in most cases, I would say if I have a higher heat input, meaning that I'm going to have a higher water temp in most cases going to any type of a heat emitter, that is going to certainly, the higher that water temperature is, the more the swings will be. And some of that is as a result of the swings. I'm going to go back to this picture here. Some of that will lead to exactly what we were talking about here, is that as we look at these applications and we change that water temperature on here, if the higher the water temp is, you're going to have much more of the temperature swings being up and down and up and down. It's harder to control a system like that. The other issue is this. The higher the mass of this emitter also leads to that problem. So this is something this is why being able to control that heat input, and generally the strategy we usually use is reset, and I'll talk about that in a little while, but that's kind of one of the ways that we do that. Let's take a look at a couple of the strategies. How do we control that heat? I'm going to go back to the handout, and let's talk about the methods to control that heat. So the first one that I'm going to hit up on here, it says describe the main elements of water flow control, and part of that control is such that, let me make this equal. Part of that control strategy is such that my heat source is we talk about the heat source is maintained at a design temp of 180 degrees. And in this case, the thermostat's going to control the system to be on or off, and that's kind of the norm. So I'm going to go back to this one here, and I'll zoom in on this one, okay, specifically. So we're talking about the control of this water, of just water flow control. The problem now with this is the way that most of the older systems were controlled, that did not incorporate any type of reset at all. So again, they're maintaining a boiler system at 180 degrees. So essentially, that in that last module, there was something called an aquastat. And your aquastat control had a setting on that control. And the aquastat control was essentially, you set the max design temp. I'm not saying the max temp that the aquastat can be. A lot of the older systems, if you said, all right, we're going to design our system for 180 degrees, then essentially what would happen in this application is every time, as described, every time the thermostat in the zone needs a heating demand, it goes over and it says, oh, by the way, zone valve, you need to open up. And then essentially the pump would start and we would move water flow. It's the simplest of all the designs as far as the flow on there. So this is 100% goes into the zone on every single heat call. It is the, as I had said, standard aquastat. That's typical the way that it works. This is definitely one where we know that when we start looking at these types of applications, that we're going to get more swings. It's more typical, it's more basic, and you're just going to get swings. And that's only because of the B2s you're putting at every emitter is essentially the max at, just like you would have design. So that's kind of one of those where, even though the hydronic systems oftentimes seem better than an air system, it still is inevitable. So we try to minimize that as much as we can. So, all right, let's take a look at the next one. The next one is essentially what we're going to call water temperature control. Now, on the water temp control, another strategy in this one here is we essentially say, all right, we're going to modulate the temperature of the water all the way from 70 degrees all the way up to the design temp. So as we're describing here, 70 all the way up to 180 degrees, let's say. And I'm assuming that we're going to use a 180 design temp. That's the assumption here. It does not have to be that. It could be 200 degrees. And essentially what will happen in this case is we would, thermostat would provide a demand, temperature remains very constant in that zone, and we would have constant circulation in this control strategy. Now, that is highly unusual. We rarely ever do that simply because it is it's so difficult to leave a system run, to always provide water flow, and all we're going to do is control the water temp. So this is rarely a strategy that really will work very, very effectively. And then, of course, we would recognize that would help with the temperature swings. They would be minimized. A more common strategy that we're going to deal with here, guys, is really going to be some sort of a water flow control and a water temp control strategy is the way that one's going to be. Now, when we look at that, what we're really doing is we're taking this strategy of flow control, number one, and we're going to take the strategy of number two, and we're going to incorporate that one, and this becomes really the more common of the strategy. And essentially the way we're going to do this is we're going to manipulate the heat source water temp in the system via a process called reset, outdoor reset temp. And we're going to allow that to go from some bare minimum temp all the way up to a max temp. It does not have to be 130. It could be all the way down to 70. It could be all the way up to 200. So there's really nothing that says you don't have to do that. The thermostat is going to control the water flow to the zone, whether it's on or off. So in other words, the T-stat in the zone says, hey, we have a demand. Let's go and tell this zone valve to open up, as an example. And that's very typical on a demand. So when we have that demand, it opens up. When that opens up, the pump starts, and the pump says, okay, let's get rolling here. And that's a kind of a typical strategy. So you will get what you need in every single demand. It is a way to really minimize the swings in the system, and it's really by far the best control strategy without a doubt. And let's go on to water temp control, and let's talk a little bit about that. So in water temp control, it's, I'm going to go to this side here on the right side, and it says, describe how my heat output is related to the water temp control. Now, in the previous module in heat emitters, one of the things that we identified was that if we change the temperature of the fluid going to a heat emitter, it will have a certain characteristic of heat output out of that emitter, is the way that it'll work. So essentially, why we do this and why we're concerned about this temperature is that the heat loss that a building experiences oftentimes is actually a direct correlation to an outdoor temp. Now, this is true in most building systems. Now, there's certainly variations, and I'll give you one of them. One of them could be if you've got a house that's at 10 degrees outside, and inside you've got it at 70, but you got a house full of people. Now, that's a variable that we really can't control in most cases. So, but if we're looking purely at the building loss of a normal system, it's directly related to the outside air temp, and that's very common in most, I would say, residential applications. Commercially, it is also somewhat of a variable. However, the internal heat gains can have a very substantial impact on that. So their curves are slightly varied a little bit, but we still use the same type of strategies even on those types of commercial jobs. Let's take a look at this slide. Now, when we talk about the temperature control, and I'm on the left side here now, and specifically, this makes sense. So if I had an outside design temp of -10, then if that were my design, we would say this is where we need 100% of the input out of those emitters to give us that. So we need 100%, and very typical. On my outside air temp, if it's 30, okay, then we need a heat loss that's maybe roughly 50%. And then if I need if the outside air temperature starts warming up, maybe I only need 25% of the demand is what we would typically need out of this system. So it's very, very typical. So what do we get from that? So obviously we know that in most residential structures and some of the commercial structures, the outside air temperature will directly demand the amount of heat that's needed from the boiler system that gets put into those units. Now, to expand on that a little bit more, the amount of, as we discovered in the previous module on heat emitters, the supply water temperature that goes to a heat emitter will have a direct impact on the percentage of the heat output. And so, for example, and it depends on the emitter. So in other words, if I have a convector, it gives you a little less output at a certain water temp. At the same water, a fan coil gives me a higher percentage. And ultimately, if it were a radiant floor system, the higher that supply water temperature, it really goes up. So they have a range. So these heat emitters all have kind of a specific range that whatever the supply water temperature is, there is kind of a max that would provide you the amount of energy that is needed, and you have to figure out where that max should be and where the minimum should be is where you kind of have to usually guesstimate. Most of the time people will use some guidance from the control manufacturers to give you a rough idea, but a lot of this is dictated based on your selection of the emitter. And it's a little bit of a guess on most jobs because you just don't know sometimes unless you're the one who designed the job. So as for example, like a radiant floor system, I've done jobs where I have my radiant floor system gives me 100% of the output on some of my jobs where I'm getting 100% of the output at 110 degrees Fahrenheit as a water temp, as an example. Now, there's other applications where maybe they don't have any floor coverings that they might be able to get that not at 110, but they might be able to get it at 80 degrees. A lot of this depends on, it's very dependent on the type of floor coverings on different types of applications, especially radiant floor. When you're dealing with fan coils and convectors, that's different. Those are more dictated, less about the floor coverings and more about the supply water temperature and how big of a unit you selected as an example. So we're going to talk water temp control. So what I want to do is specifically hit up on a couple of little things on this water temp control. So I'm going to just slide this one on over. Now, water temp control, there's two types of control that we use that I want to point out here. The first one that we're going to use is essentially going to be what I call a partial outdoor reset. Now, I want to explain this, and this is probably one of the most important ones generically that you really need to understand as far as why we want to do this. Now, what we're doing with this type of control is with this partial auto reset is we are going to have, in most cases, some sort of an outside air temp sensor, and that's primarily because in a system where we feel the outside air temperature dictates the heat output needed, that's a good input. So that's going to be an input that has to go to the boiler system controller, or whether it's a boiler or a generic controller that might be available, commercially. Now, what will happen now is the other input that has to be there is this one, is supply water temp. Now, we could do supply water temp. We probably could also do return water temp. The more common way to do it is looking at supply water temp. So what will happen then is there will have to be a sensor installed directly on the supply water temperature, leaving the boiler, or you could even say leaving the system. And it varies depending on the system that goes on here. All right, now there will also be some sort of a let's call it a curve, and what dictates this curve. So specifically what I want to do is on every one of these systems, you're going to have a temperature that you are going to identify that happens to be the point where we say, well, this is where I want to shut my boiler down. And sometimes we'll call it a warm weather shutdown point. And that really is the warmest temperature at where you no longer want to allow your boiler to function. And it'll actually be disabled for any type of a heating demand that is not domestic water. And I'll talk about that later. As we look at this whole curve and we identify our warm weather shutdown point as a programmable function within your controls, there will be kind of this curve, and you'll also identify what you feel is the max temp. So let's say if my outside design is at -10, and at -10 maybe we determine that the max temperature that we want at -10 is maybe 190 degrees. Now what will happen then is by identifying the 70, by identifying, or 60 or 65, depending on what you feel, and your outside design temp. I'm just giving -10 as an example. There's some applications you may have to set it at 20 below or 15 below. It depends on what you use as your design temp. What we do then is we essentially identify the max temp that we want the boiler to work at and the minimum temp that we want to do. Now, what makes it partial auto reset is the fact that we're going to, at -10, we're going to be at 190. At 10 degrees, we're going to change that water temp. So we're going to progressively change it. So every time that it gets warmer outside, our supply water set point is being manipulated, or what we call reset. We're resetting the supply water temp. And as we continually progress through that, and it gets warmer outside and warmer outside and warmer outside, we're determining that will change that water temp that we're going to deliver out to the zones. And that's essentially what they call outdoor reset. Now, what makes this partial in this case is that we're going to only let it go down to a certain temperature. So we might say we do not want a supply temp any lower than 130. Now, some boiler manufacturers might say if it's a cast iron boiler, do not go less than 140. Some might say 130. You have to figure that out. I use kind of 130 as like a bare minimum for most of the boiler systems that are high temp cast iron boilers. Things that are steel, that I have to concern myself with the acid from condensate, that is going to create a problem for my boiler. So you might determine that, you know what, I'm going to set 140 or 135 or 125. You have to figure that out. 130 is actually, I think, a pretty safe number, to 130 to 140. I've had commercial boiler systems guys come out, and when I'm doing control work on a commercial job, and those guys would specifically say, I don't want any less than 140. I think that might be pushing it a little bit, but that's what they wanted. So as long as that boiler was under warranty, we had to pretty much set that the lowest temp we would allow to that 140 degrees in that case. All right, now that right there. So now what happens is, let's go back to this point right here at 130. So on this system, we're showing it, this is going to occur at 30 degrees. Now at 30 degrees outside air temp. Now, no matter if it gets 30, 40, 50, 60 outside, it will not let that boiler minimum temp go lower than that. So this right here, this is going to be a parameter that you oftentimes will have to put in, depending on the boiler system. And again, what I want to point out here is in this little picture, you notice how they're showing a little water droplet, and they're saying, and with a slash in there, what they're talking about is non-condensing. So this is going to be true of any non-condensing boiler system, is where you would use something like this. So you have to dictate that parameter and do that. So it's again, very typical of most commercial applications. Whoops. Okay. Well, let's take a look at what full outdoor reset might look like. Now, in a full outdoor reset, what I want to point out to you is everything stays the same, where you have to have, so you got to have some measuring tool or measuring sensor that's going to look at supply water temperature going out. You have to have some sort of an input. Maybe it's outside air temp is what we would have. And then, of course, that's going to allow us to say, okay, I need you in the programming to tell me what is your outside design temp, and maybe that happens to be minus 10. And you're going to tell me, okay, at minus 10, what do you want for a water temp? Well, I want to have, and they might not specifically say minus 10, what do you want the water temp? What they're going to say is, so you set up your design outside air temp in some situations, and you set up the design supply water temp. It's assumed that you're going to know that at minus 10, you're going to want to have the 190, is the way that they're going to make that assumption. Now, and then obviously, based on the other input, what they're going to do is based on the other input is going to be your inside temperature, or what we call the warm weather shutdown point, and that could be, they might change the terminology where it's like, well, they might say off point or something like that is what they might do. So those are ways that we'll have to look at it, but that's a great way that this can be done to do that. Now, what type of system is this for? This is definitely going to be for a condensing boiler. Okay, and it could also be used for a system where we can do full reset out into a system using some sort of a mixing device. Now, and a non-condensing boiler. Now, when we do that, that's what they're describing here. So this could be a system where we say we're going to use partial outdoor reset, like we had up here for a non-condensing boiler, but we're going to do full outdoor reset out into my system. So this is where this mixing device, like a three-way mixing valve that automatically changes the supply water temperature, and it goes out into the system at something lower than what it was at partial outdoor reset. So in this example, what we're doing is we're saying we're going to take this area that we lost control of, and we said we're not going to go lower than that for the boiler. And what it allows us to do is say, okay, we're going to take that area and we're going to let you continually go down. So that means now at 50, we're going to say, all right, I'll let you go to 100 degrees at 50. And at 60, we might say, well, we'll go down to 80. You have to identify all those points. But that's an example a little bit on the reset, on outdoor reset. It's a really super common application that is used commercially, as well as residentially. Almost every single brand new boiler system has this type of control actually built into the system. So your control system, whether it's an IBC boiler or a triangle tube or a Well-McLean, most of these types of systems, almost all of them, have boiler reset built into them if it's any type of certainly a condensing application, but any of your more advanced modulating type boilers all have this built into them. Looking at a couple of other things here on the water temp control. From an efficiency standpoint, it certainly benefits the system. I would encourage everybody that is, if you're ever putting in a condensing type boiler, this is an absolute necessity. A boiler system that is a condensing boiler will benefit in every single way by being able to limit the supply water temperature constantly to try to make sure that, hey, if it's warmer outside than the design temp, we do not want to be sending out that high temp water out into those emitters. So that's kind of the big thing on there. So very important on the overall efficiency. Just a few notes that I had made on here, just to recap what we had just talked about. Talked about the heat output from the terminal units is directly related to supply water temp. Very true. The operation of partial outdoor reset is outdoor reset changes the supply water temp. It changes supply water temp. Okay, SWT, I'm calling that based on outside air temperature input. There is such a thing called a heating curve is established. And when you program those parameters into most boiler system controllers, what you're doing is you're setting the high and the low, and it figures out the ratio all in between. You don't have to actually go in there and change and input, hey, I need to have, what is it going to be at 180? And what is it going to be, what is it going to be at 70 degrees or 75 or 50 degrees outside and 60. You don't have to go in there and do that. You set up the 2 points and it figures everything out. It figures what we call the curve. So heating curve generally is done automatically. There are some situations where what we're saying is the heating curve is either manually set or automatically curved. So the manually curve, what I'm describing here is where you tell the high and the low points. Automatically is where when you set up, there are some manufacturers like Tecmar that does this, where you set up, hey, this is the type of emitter that I'm using, and this is the type of boiler I'm using. They will automatically figure out where those high and low points as a default. That's what that means. So the partial outdoor reset will lower that supply water temp down to a predetermined minimum that you have to determine. The whole reason is this: flue gas damage. So we do not want to have that issue. And then obviously the minimum temp I describe is normally in that 130-ish to 140-ish for most non-condensing. And then your reset ratio, that's essentially calculated by your delta T of the water temp change divided by the delta T of the outdoor temp change. So I'll give you an example of that. So commercially, on the commercial controllers that I've dealt with in the field, my typical delta T on the water temp change might have been 180 minus, let's say 120. And that has a change of 60 degrees Fahrenheit. Okay? And then the outdoor temp change might have been, let's say, an outside design temp of maybe 0, as I'll use that as an example. And let's say 0 minus, let's say the warmest you're going to run is, let's say, 60 degrees. At 60 degrees outside, I might not want to use my boiler anymore. Now, in that case, that gives me a 1-to-1 ratio. So that means every time that we are in between the 0 and the 60, we are going to see a 1 degree change in every one of those as we progress down. Now, if I were to change this one to, let's say, I'm going to use 180 minus, let's say, 80, that would give me a 100 degree change, okay? And I might let's say I use minus 10, minus 10, all the way down to, or we'll say to 70 degrees outside. Now that's a little warm for me, but I'll just use that as the example. So that would give me an 80 degree delta T. So now my reset ratio, what I want to describe to you is this. We're going to take the change in water temp, in this case that'll be 100, and we're going to divide that by the 80. Now when we do that, that is going to give us what we call kind of this ratio of X amount to 1. So we'll calculate that out. So 100 divided by 80, and that equals 1.25. So we're going to have a 1.25 to 1 is what we're going to have. 1.25 to 1 ratio. So you have to, that's something that whatever control system you happen to be dealing with, you need to learn how are they wanting you to identify that. And then of course with full auto reset, we recognize that the operation is the same as the partial auto reset, except we took out the minimum. We let that thing go all the way down to what we would consider as the lowest water temp we want to achieve on a boiler. And again, that is a programmable feature by most applications. I talked about it being condensing boilers and non-condensing boilers with a mixing control. That's your other applications. And then essentially the warm weather shutdown point is the key point in there. So you have to figure out what terminology that manufacturer might be doing with that. And that's typical of most service techs are going to have to identify where that point is. So that's and that's dependent on the manufacturer of the system. And obviously that'll be it. So what are the benefits from this? It is crazy good how if you change that supply water temp, how you don't get these temperature swings. You end up getting a lot better efficiency out of your system. You end up getting a very good, you actually minimize your heat loss in some situations. And I'll give you one example specifically. If people that have in-floor heating in their basement and they're running water temps that are too high, they will have higher heat losses through that floor than what they should be getting. So if you can control that system to the least amount of energy, you will benefit by that. So if we can lower that in those in-floor heating jobs to the least water temp that you need, you're going to benefit from an efficiency gain on there. So very, very good. This is something, again, full outdoor reset or outdoor reset. It was primarily used commercially, and then it was really in the last 10 to 15 years when energy has been even a bigger deal, that we've been seeing it pushed into all the residential side of things as well. And I'm so glad that the boiler manufacturers have really taken hold of that and said, let's incorporate this into our systems. And that's been going on for some time now. So very, very good. So that was the first section. I'm going to pause here to take a small little break and break up this little PowerPoint.